A hydroelectric power station uses the gravitational potential energy of water to generate electrical energy. In, in one particular power station, the mass of the water flowing per unit time is 1.5 into 10 to the power 5 kilograms per second. This is mass flowing per unit time. So this thing is m divided by t. 1.5 into 10 to the power 5 kilograms for the mass and s minus 1 for the second. So the collective value of mass divided by time is given as this much, aka this thing is also known as mass flow rate, or, or mass flowing per unit time. The electrical power generated is 100 megawatt. What is the efficiency of the power station? So can you give me the formula of efficiency in terms of the power? So one of the power, the useful power from the generator is the electrical power. So the electrical power generated by the generator is 100 megawatt. So mega stands for 10 to the power 6, which is equivalent to 1 million. So I can write it as 100 into 10 to the power 6 watts. Now the question is this output power or the input power for the generator? Output power. So what do we need to find? We do have the value of the useful output power, which is the electrical power. We need to find the value of the input power. And what we're using is we're giving the gravitational potential. We're using the gravitational potential energy of the water. Can you give me the formula of gravitational potential energy? If I'm going to divide the gravitational potential energy, if I divide the energy by time, and I'm dividing both sides with this thing, now energy per unit time, or the rate of the transfer of energy, is power, and that equals to mgh over t. Now what do we have from the data? Do we have the value for g, which is 9.81? We don't even need that in the question. Do we have the value for height? Yes, water falls through a height of 120 meters. Do we have the value for mass and the value for time? And the thing is, we don't have the individual value for mass and time. We have the collective value for this thing, m over t. So instead of m over t, I'm going to write the value for m over t, which is 1.5 into 10 to the power 5. So this is a collective value for m over t, which is called mass flow rate or mass flowing per unit time. G equals to 9.81, H equals to 120. Please hit it on the calculator. 1.76. So this is the input power, and you see the input power is greater than the output power, and it should be this case. So I'm going to insert the values. P output was 100 times into 10 to the power 6. You can also write it 1 into 10 to the power 8, would mean the same thing, divided by the input, which is 1.76 into 10 to the power 8 times 100. Can you hit it on the calculator once again quickly? So this should be into SF, we can say 57. So C is the right answer for this one. Are we clear with this?
Yes, sir.
A car of mass 1100 kilograms is traveling at a constant speed of 15 meter per second. So I told you something about the constant speed in the prerequisite. You'll have to link that concept over here. And secondly, we're moving up the slope. So it is pretty much the same case as the case of the inclined plane. So it is the same diagram. The box is replaced by the car. The angle we used to use like 60 or 30 degrees is now 10 degree. The combined frictional forces acting on the car are directed down the slope and equal to the fifth part of the weight. Okay, so here we have the frictional forces. So isn't that the same thing that I told you? There could be frictional forces as well, and then you have to compensate for the friction as well. So if the car is moving forward, there would be frictional force backward, down the slope. Backward mean down the slope. And the frictional force is mathematically how much? It is fifth part of the weight. So can we find the value of the frictional force first? Yes, we can. It is fifth part of the weight, but then W equals to mg, right? And we are provided with the mass. Mass is provided as 1100 times 9.81 divided by 5. Can you hit it on the calculator quickly? A force that would try to oppose the direction of motion. My follow-up question is, this is a force that is against the motion. Is there any other force that is trying to drag the vehicle down the slope? The entire force of gravity, which is mg, so you see this one would be mg, the entire force of gravity. But would that be in the entire force of gravity or one of the component? And if it is one of the components, then would it be mg sine theta or mg cos theta? Yes, it is mg sine theta. Once again, you have to consider this for a fact that if this is the angle theta, then the component that tries to drag the object down the slope is mg sine theta. Okay, it's always going to remain the same. Sometimes mg sine theta could be in your favor, sometimes it could be against you. Could be in your favor if you're going down the slope, then the mg sine theta is actually helping you. But if you're going up the slope, then mg sine theta is against you. So you'll have to supply a force, that is the forward force, that would make the vehicle move forward. We can call that force of the engine, because that force comes from the force of the engine. And we need to find the useful power of the car's engine. So one of the formula for power in terms of the force is power equals to product of force and speed, P equals to Fv. Question is, how much force should be applied by the car engine so that the car can move up the slope with a constant speed? What is going to be the sum of the backward forces? This thing, F, the friction force, plus mg sine theta, because both of them are backward. Now we can insert the values. 2158 plus, we can calculate mg sine theta. So this one would be 11,000. So 1100 times 9.81 times sine 10. Can you hit it on the calculator like real fast? The force that the engine has to supply to make the vehicle move with a constant speed. But we need to find the power. So power is a product of the force, which is the force of the engine, because we have to find the power of the engine. So that equals to the force of the engine times the speed of the vehicle, which is 15. Hit it on the calculator. So here we have the next question. A train of mass this much is moving at a constant speed. So I'm going to highlight this thing. It's moving at a constant speed up a slope inclined at an angle of 0.64. So it's moving with a constant velocity. because it's moving at a constant speed in a straight line. The angle is given as, oh, such a small angle, 0.64 degrees. And the engine of the train is producing the useful power of 14 megawatts, which is 14 into 10 to the power 6 watts. Assume that there are no frictional forces opposing the motion of the train. Okay, such a relief. We don't have to compensate for the friction. All the engine has to do is to apply a force just to compensate for only one thing. And I'm going to ask that question from you. So if the weight of the train is mg, all right, and the train has to move up the slope, and the engine is able to produce the power of 14,000, so P equals to power of the engine is not 14,000, why do I keep saying that, 14 million watts, or 14 into 10 to the power 6 watts. The speeds needs to be found out, and the force, if we can find the force, then we can use the formula P equals to F into V for the car's engine. So P is already there, force we can find it, and then we can answer for the value for speed. Now the big question is, how much force has to be applied by the engine of the train so that it can move up the slope with a constant speed, knowing that there is no friction? So what does the engine need to compensate for? Which force needs to be compensated? So even if there is no friction, but since you're going up the slope, so mg sine theta is going against you. It is the component. So I'm going to say it fourth time today. The component of weight that drags the object down the slope is mg sine theta. If this angle of inclination is theta, then the component of weight that drags the vehicle down the slope is mg sine theta. So the engine force has to match up with mg sine theta, and then you can move up the slope with a constant speed. If the engine is applying a force less than mg sine theta, then the train would be going down the slope. And if the engine is supplying a force greater than mg sine theta, then the train would accelerate. But we have to move with constant speed, so we have to supply exactly the same force. Force has to be equal to mg sine theta. So whatever the value of mg sine theta is, that would be the same for the value for force. So we can find the value of mg sine theta. So what is mass? 3.3 into 10 to the power 6. G is 9.81 times sine theta would be sine of 0.64. Could you hit it on the calculator? Which in 2SF can be written as 39. So C is the right answer for this one. Let's move on to the next one. Okay, now we have the questions of the energy changes, all of them. So let's start off with this one. So here we have the next question. And a bead is released from rest at point P and slides along the wire. The track loops around and forms a vertical circle of diameter 40 centimeters. At point Q, the bead has a speed of 1.4 meter per second. We can see exactly the same thing on the diagram. There's no friction of any kind, what is the height from which the bead is released? Okay, so it should be an easy one. At this point, because it starts from rest, you can call that point P. So the energy at point P should equal the energy at Q. Okay, this is what I explained in the energy conversion diagrams. The case is whenever the object starts from a higher point towards the lower point, you can always start the answer or start the working with this thing. Energy at that point equals to the energy at the lower point. And whenever the object starts from a lower point towards a higher point, then you can write the expression in terms of the work done. These are two similar things, matter of fact exactly the same thing, but it would be better for you to understand this way. So what is the energy at point P? The kinetic energy is not there, it is at rest. And what is the energy at the point Q? GPE, first of all, plus kinetic energy as well, because the ball is still moving. Okay, so at the point Q, there are two energies. One of them is GP because the ball is still at a height of 40 centimeters off the ground and it is still having some speed 1.4 meter per second. So it has both the energies. Now what is the expression for GP is mgh equals GPE on the other side, which is m. Are we provided with the mass? No. So I'm going to write m as it is, and g is 9.81, and height on the point Q is 0.4. Okay, it's 0.4. You can see it for yourself. Over here, 40 centimeter would be 0.4 meters. Plus the kinetic energy, which equals to 1/2 times m times the square of the speed. What is speed? 1.4. Then you can take square of the speed. Can I take m common from the right side? Cancelled out with the mass on the left side. Okay, we'll just skip one of the step. Now g is 9.81. 9.81 times whatever the height is equals, now you'll be needing to use a calculator. Can you sort it out? 9.81 into 0.4 plus 0.5 into 1.4 square. A railway engine accelerates a train of total mass 800 tons, and 1 ton equals to 1000 kilograms from a rest to a speed of 50 meter per second. So the speed is 50 meter per second. How much useful work must be done on the train to reach this speed? So at the start, you'll have to do the work done, and the work done would be converted into other forms of energy. What do we write? We write change in kinetic energy. This is the general expression, plus the change in gravitational potential energy, plus the work done against friction. Okay, this is the standard expression for all cases. We need to find this work. We need to find this thing over here. Now, as a car moves from rest to a speed of 50 meter per second, would there be any change in kinetic energy? The answer is obviously there would be. At rest, the kinetic energy is 0. And at a speed of 50 meter per second, there would be some kinetic energy. So the change in kinetic energy, since the initial is 0, would simply be the final kinetic energy, mv square. Are you moving up the slope, or are you gaining some height as well? The answer is no. So change in gravitational potential energy, 0. Is there any work done against the friction that is mentioned in the question? Once again, the answer is no. So the entire work would equal to the change in kinetic energy. So 1 over 2 as it is, mass is 800 times 1000, so that would be 800 tons, times v square, which is square of 50. Could you hit it on the calculator quickly? For 9, okay, so it should be C, right?
Yes,
So
sir.
C is the right answer for this one. Once again, we're moving from a higher point towards a lower point. And I'm going to just take a look at the diagram, and we can see we are starting from rest because the initial speed is 0 and the final speed is 11 meters per second. The vertical height is 30 meters. The distance covered is not given from x to y. We don't know how much distance is covered. What is the energy dissipated by friction forces where the car moves from x to y? So do we need to find the value of Wf, which is the work done against friction? And what you can
Yes,
write
sir.
is likewise to the previous one. Whenever you start from a higher point, you can always write the expression energy at P. In this case, energy at X. I mean, what form of energy is there? Only GP plus kinetic energy, or which one?
Only GP.
Okay, only GP. Thank you. So GPE. Kinetic energy plus there is some other one as well. Work done against friction. Because as the car travels down the slope, there would be some air resistance and you have to overcome that as well. So you'll have to do the work against the friction. It, it could have been there in the previous case as well, in the question where the train was moving forward, but in the question they did not mention about the air resistance, about the friction. So we did not have to compensate for friction. In this one, they say what is the energy dissipated by the friction forces. So the friction forces are there. So GPE on the left side would be mgh. I'm going to insert the values. Mass is 500, g is 9.81, h is 30, equals to 1 over 2 mv square, 1 over 2 into 500, and the speed is 11 square of it, plus wf needs to be found out. So I hit this thing on the calculator and subtract this thing on the left side. A rope is attached to a sled and the boy uses the rope. Okay, the diagram is there. How much work does a boy do on the sledge when he pulls it a distance of 5 meters along the surface? We need to find the work done. So work done. What is the formula for the work done? F into D. Provided the distance or the displacement is covered in the direction or along the line of work. So if the force is being applied in this direction, let's say along the x-axis, it could be forward or backward, then the distance has to be covered in the same direction on the same line, could be forward or backward. Even if they are opposite, it would work with just multiply force and distance. Basically the force and distance has to be parallel, and when I say parallel, it could mean anti-parallel as well, which is just a type of parallel. So the force and the distance covered have to be in the same line. But you see, the distance is covered in this direction. Let's say this is a point X, and then the boat moves towards a point Y through a distance of 5.0 meters. So distance is there, but the distance is in this direction. The force is not in this direction. So what do we do? Now we recall that tool that I explained you previously that we call the resolution of the vector into components. So this is your vector 100 Newton. You can resolve this vector into two components, and one of the component would be along this line where you want the vector, and the other component would be perpendicular to the first one. So we are using the same strategy here, which is resolving the vector into components. And matter of fact, we spend a whole lesson on to this thing, and you see this is where we use this thing, resolving the vector into components. Now one of the component should be in the desired direction. What is the desired direction? The direction in which the distance is covered, so we can find the work done. And the other component would be perpendicular to the first one, and the one in the direction of the distance would be mathematically 100 cos 30 or 100 sin 30. Which one of these two?
100 cos 30.
Exactly. And how do you remember this?
The one with the angle is always cos.
Yes, that's the rule. One with the angle is always cos. So can we find the value of 100 cos 30? So instead of taking the full force of 100 Newton, will we only use a component of the force, because only one component of the force is actually aligned with the distance. And how much is that? It is 100 cos 30. Or you can find the value first and then plug it over here. And the distance covered was 5 meters. So cos 30 would be 0.866. So here we have this one. The weight of the block is given as 80 Newton. So that would be the product of mass and 9.81, the gravitation field strength. The distance covered is 60 centimeters from point X to, let's say, the point Y. The distance covered is 60 centimeter, and the slope is 30 degrees. So it could be something like this, 30, and let's say the starting point is from point X. I can draw point X over here, point Y over here. From point X towards the point Y, it would be 60 centimeter. Well, the thing is, point X is not at the ground level. So let's say the point X is at this point. So it is 60 centimeters. Now the first thing, we need to find the work done against the gravity, and then we need to find the work done against the friction. So the work done against gravity would equal the product of the force and distance. Which force? The weight times the distance. Which one? The vertical distance. Or basically we're using the formula mgh. When you lift an object, or when an object is at a certain height, then the work done against the gravitational force, to bring it to that point, the work done against the gravitational force equals the increase in the potential energy. So the collective value of m and g, aka weight, is given as 80. And what is the height, the vertical height? The answer is, right now we don't know. So what we can do is, I can draw a small triangle here like this, and this is a height that needs to be found out, and this angle would be 30. Okay, because I've drawn the parallel line with this one. So if I know the hypotenuse and I know the angle, can I find the perpendicular?
Yes.
The hypotenuse, we don't even need the base. The perpendicular is there, and we need to find the perpendicular. The angle is there. So sine theta equals to perpendicular over hypotenuse, and sine of 30 equals to x, which is the height, divided by base, hypotenuse, which is 30. And in this case, x would be, since it is 30, then hypotenuse would be twice, so it would be 30 centimeter. But you can hit it on the calculator, check it out by yourself. Sine 30 would be 0.5.
Yes, sir, it's 30.
So I'm not going to write 30 here, rather I'm going to write 0.3, right? So what do we get? We get 80 times 30 would be 2400, then divided by 100 would be 24. So we get 24, right?
Yes, sir.
So the work done against gravity would be 24 joules. So it has to be either A or B. Now the next thing is, what is the work done against the friction? So the work done against the friction would be the frictional force times the distance covered in that direction, which is very easy in that case. Why? Because the friction force is there and the distance covered along the line of frictional force is also there. So if the box is moved forward, the friction force is in this line, the distance of that line is also given. So what do we write? 25 times, not 60 but 0.60. Alright, so for this one, a cyclist is traveling at a constant speed up the hill. What else? Okay, so we need to find, we're moving at constant speed. So the forward forces and the backward forces, their sum should be equal. At least we know this thing. And that covers a distance of, let's say, he has to cover a distance of, from starting point to the end point, he has to cover a distance of 20 meters. We need to find the increase in gravitational potential energy of the cyclist. So what I want is, if you could help me out with this one, like where do we start this kind of question when we are moving from a lower point to a higher point? How do we write the expression for the energy or the work done? Okay, thank you. I'll add just another thing here. It is actually the change in all these energies, the change in kinetic, the change in gravitational potential, and the work done against friction. So delta KE plus delta GPE plus work done against friction. And they found the work done by multiplying force and distance, and the answer was 450. So can I write, instead of work done, can I write the cyclist uses 450 joules of energy? So the work done would have been 450 joules. There won't be any change in kinetic energy because kinetic energy equals to 1 over 2 mv square. So mass is not going to change, first of all, and the speed is also constant. So at every point the kinetic energy would same. Let's say if the kinetic energy is 100 initially, then at every point the kinetic energy is 100. Now what's the change in kinetic energy? 0. That's why once you stated the expression, I added the extra thing that it's not the kinetic energy, it's the change of kinetic energy. Likewise, the change in potential energy. Well, for potential energy, the initial potential energy was 0, so the change in potential energy automatically equals to the final potential energy. So instead of this thing, I'm going to write 0 plus the change or the increase in GPE. We need to find it. Now what is the work done against friction? Should it be the frictional force times the distance covered in the direction of the in the line of the frictional force?
8 times
How
20.
much? Or uh, 8 times 20, yes. Plus 8 times 20. So what do we get?
290.
290. So this is the answer for this one. But let me do just a bit of commentary on this one, and then we'll be done with this. The work done, the work that was done by the cyclist. I'm discussing this thing. We wrote this thing down as 450. But what you said, the formula would have been the forward force of the cyclist, which in this case you can call it the driving force, the force of the engine. It's not exactly the engine, but would be essentially the same thing, the forward force, the driving force. So the work done would have been equal to the driving force and the distance. Distance we already know is 20 meters, right? And the forward force was not given. In matter of fact, whatever the forward force was, they multiplied that forward force by 20. And what answer do we get? We get 450. So can you find me the forward force? Now my next question is, the cyclist has to move forward. You can call it driving force or the force of the engine, whatever you want to call that. The forward force has to be 22 Newton, 22 and a half Newton. But the frictional force is merely 8 Newton. Listen to the question very carefully. The forward force is 22 and a half Newton, but the frictional force is merely 8.0 Newton. And if the cyclist has to move with a constant speed, then the forward and the backward forces should be equal. So why does the cyclist need to apply a force more than the frictional force? What is the need for the cyclist to apply the extra force? Would he move upward if the driving force would have been equal to the frictional force? Don't you see, in that case, if the two forces are equal and opposite, then there is no resultant force and we can move with a constant velocity or constant speed in a straight line. But the cyclist has to apply a force greater than the frictional force, means he needs to apply force for some extra thing as well, to compensate for another thing as well. Can you tell me what is that other thing that cyclist needs to compensate for?
mg sine theta.
Exactly. Excellent. So that is mg sine theta. So there was some slope, and the poor cyclist, he had to compensate for mg sine theta as well. So mg sine theta, he had to compensate for mg sine theta and for the frictional force, and he needs to apply the same force equals to the sum of these two. Then let me ask you the next question. Can you find me the value of mg sine theta, the collective value of mg sine theta? Write the expression like this: forward force, which is the sum of forward force Ft, equals to the sum of backward forces, and the backward forces are 2, which is mg sine theta and F.
Yes.
Now can you find me the value of mg sine theta from here? 14.5, 14 and a half Newton. So this is the force that was trying to drag the vehicle down the slope. And that's why the cyclist had to supply or apply a force greater than the friction, because it's not only friction that is going against us, it's mg sine theta as well.